Alright guys, if you remember with the TKIP, TKIP is the short-term solution. It does use two keys. Okay, one key for 128-bit key is used for the mixed function. This is your actual key that is going to be mixed within the mixed function, and then it's going to go to RC4 algorithm, and it becomes an RC4 key, and RC4 is going to generate a key for the actual encryption, if you remember. Okay, and then 64-bit key used by Michael. Okay, and we are using this for MIC calculation. So in other words, message integrity code will be calculated by using 64-bit key length, and the algorithm is going to be Michael. Okay, Michael. So these keys are going to be fresh with each association every time. So when you have a new association, you're going to have new keys definitely. Okay, and how are we going to manage these things, these keys? How are we going to distribute those keys? It's going to be IEEE 802.1x. If you remember, we saw the packet sequencing for that one, and then they are actually generating all those keys by using this IEEE 802.1x protocol. Okay, so keys are going to be generated that way, and now we will be able to use these two keys. One is 128-bit key, and the other one is for 64-bit key for Michael. Okay. So as I said, this was a short-term solution, TKIP. What was the long-term solution? If you remember, it's called CCMP. Okay, it's called CCMP. So it is in the counter mode CBC MAC. So this is the counter mode operation. Merges two well-known and widely adapted technique basically. Okay. One is counter mode. Do we have any idea about the counter mode? If you remember, I explained that one to you guys last week, I guess. There will be counters, okay, and there will be encryption algorithm right here, okay, and then either plaintext is going to be XORed with the counter, or counter is going to be encrypted, okay, with the key. And you're going to have another key that is going to be encrypted with that's going to encrypt your plaintext. So in other words, we're going to use the counter values to generate the keys. Actual encryption is still exclusive OR. If you remember in TKIP, we generated this key by using RC4, right? But here we are going to use a different algorithm. Okay, this mode, where you use the counters like this, okay, this mode is called counter mode because you're going to have a lot of counters like this. Is going to be encrypted, counter is going to be encrypted, counter is going to be encrypted, okay. So this way, what you can do, why they are using this mode, that I'm trying to explain that one. Imagine that you need a high-speed encryption, okay. For high-speed encryption, you have to, if you have this kind of feedback mechanism, you have to all the time wait the first encryption and do the second encryption. Okay? But you have to wait for the first encryption to be completed. But in counter mode, you don't do that. Okay? In counter mode, every block of the plaintext, okay, can be encrypted independently because key generation does not depend on previous keys, or encryption does not depend on previous encryptions. Okay, previous encryptions. So that is the idea. That makes the system so fast because these keys that is going to be used in encryption can be pre-calculated, okay, based on the IV values. So when you get the message, your keys are ready. All you have to do is just XOR those keys with the blocks of plaintext, or with the encryption of the plaintext. Okay, so that is the idea behind the counter mode. You can do encryption faster. So it is fast, in other words. Okay, it is quite fast. So if you go and click on that link, you will see the actual diagram of the counter mode. So they use counter mode for encryption. Okay, and they use cipher block chaining. Cipher block chaining means, what I'm going to do is, let's say that this is my plaintext, okay, and I'm going to encrypt that plain text with the key, okay, with the key, and let's remove this one over here, and I got the ciphertext, okay, I got the ciphertext, but this is for the first block of plain text. This ciphertext is going to be exclusive OR with the second plain text block, okay, and it's going to be encrypted. So this is going to go like this, okay. So next encryption, next block encryption, I should say, depends on the previous encryption. Okay, depends on the previous encryption. So in other words, previous encryptions are going to affect the next encryptions. That's called CBC mode. Okay, cipher block chaining. So we are chaining them. Okay, we are making each other independent to each other, basically. Okay, and they are going to use this for MAC calculation. If you remember the definition of MAC and definition of hash functions, MACs are fixed size outputs. Okay, MACs are fixed size outputs. And the input to those outputs are the plain text and the key, secret key. So MAC is a fixed output, is a function of input plain text and secret key. Okay, secret key. So imagine that you are doing this kind of calculation and every time you are generating a ciphertext block. So what we're going to do is, we're going to get the last ciphertext block and I'm going to use that last ciphertext block as MAC. Okay, last ciphertext block is going to be used as MAC. It is fixed size depending on the algorithm. If you are using this algorithm over here, each ciphertext block size is 64 bits. If I am using AES algorithm, each block, ciphertext block size is 128 bit. In other words, last block size over here is going to be 128 bit if I am using AES. Okay, if I am using AES. So this is called CBC MAC. Again, if you click on this link, you will see the whole diagram over there for this cipher block chaining. This cipher block chaining. So you see they are using two major technology. One is counter mode, very fast encryption, and the other one is cipher block chaining, okay, for MAC calculation. And the good thing over here for this CCMP is encryption algorithm and the MAC algorithm is the same. Okay, I'm going to use AES algorithm, Advanced Encryption Standard. Okay. The name of the actual algorithm is called Rindell. The other one is Advanced Encryption Standards. Okay, the name of the algorithm is Rindell. And we are going to use AES in counter mode for encryption, and we're going to use AES in CBC mode for MAC calculation. So I don't need any other extra algorithm, okay, to calculate MAC. So when I have one implementation of AES, I'm going to use it for encryption, and I'm going to use it for MAC calculation. Isn't that nice? You see? So these guys are designing it this way. So both algorithms use only the encryption primitive at both sender and receiver. Okay? And use the same key for both. That's also other thing. Confidentiality and integrity. So I don't need any MAC key extra, separate than the encryption key. So encryption key is going to be used for encryption and for MAC calculation. So this also reduces the complexity or the management of the keys as well. If you remember in the previous technology in TKIP, we were using two different keys, 128-bit encryption key, 64-bit Michael key. Okay? But over here, I don't need those two separate keys. One key is going to be used for confidentiality and MAC. Confidentiality is going to be the encryption, or encryption is going to provide the confidentiality service. MAC is going to provide the integrity service. All righty. Okay, let's have a look how we're going to do all those things. First of all, we're going to have a packet sequence number. Okay. And this is my plain text, and this is the key that I'm going to use for encryption and for MAC calculation. Okay, let's have a look. So I'm going to have a construction of IV and counters. Okay, counter is going to be used for encryption. IV is going to be used for the CBC mode. Why do we need IV in CBC mode, guys? Imagine the first encryption. And we said that every part of the encryption depends on the previous encryption, right? In CBC mode. Where is the previous encryption for the first encryption? We don't have it. So what I'm going to do is I'm going to generate a random number, which is IV. That's going to be the previous encryption of this. So that IV is going to come right here. Okay? That IV is going to be XORed with my plain text, and it's going to be encrypted. Okay? That's why I need IV. That's just because of CBC mode. Okay? If you look at the details of CBC mode, you will see that IV over there anyway. And the counter is counter values for the counter mode. Okay, for the counter mode. Okay, we're going to encode the packet with sequence number. So in other words, every packet is going to have a sequence number. Why we need the sequence number? Any idea? We discussed that one before. Why we are using the sequence number? Come on. To avoid replay attacks. To avoid replay attacks. Every time we're going to use this kind of sequence numbers to avoid replay attacks. So by checking this sequence number, you will understand that received packet is a new packet, fresh packet, or it is an old packet replied by someone else maybe, I don't know. Okay? So that's why I'm going to reject it. Every time I'm going to use a random number as a packet sequence number to avoid replay attacks. Okay? That is very important in security anyway. We are using this kind of sequence numbers in TCP/IP protocols, right? Why you are using it? Again, if you lost any message or something like that, you can understand that this sequence number packet got lost. Okay? Or if you get a double packet with the same sequence number, you can say that, hey, this is a duplicate packet. I'm going to reject this packet. So same kind of logic is going to be used in security totally, overall. We call them nonces, by the way. Okay? Nonces. So we're going to use those nonces, those random numbers, those sequence numbers to make the packet unique. Okay? Unique. And I'm going to keep the list of all the received packet sequence number from that particular source. So that if I get the same sequence number, okay, for the next packet, for example, I will immediately understand that that next packet is replay of this packet. So that I'm going to reject that one. Because what is important in security is this. Okay, let me give you one example so that maybe you can understand what I'm saying. You are withdrawing money from ATM machine. Right? Did you check those ATM machines? They are pretty secure right now, but in the past, the cables just behind the ATM machines were open. Okay? Imagine that you tapped over there, okay, those cables, and you are recording the transaction that someone is, while someone withdrawing money. Right? You can do that. It's not a very big high-tech stuff. The only thing is that you have to tap that communication link. Okay? You record it, and that guy withdrew the money and left. What you're going to do is, you don't have the card or anything, but you have every information exchange between ATM machine and the whatever the server over there. Okay? And you replay the transactions, or you replay the packets that is recorded. What's going to happen? Are you going to be able to withdraw money? That's a good question, right? Well, you may, okay, if there is no protection mechanism. But right now, with the sequence numbers, they will immediately understand that this is a replay. You are not going to be able to withdraw money. You are not going to be able to withdraw money. They are going to have new session IDs, first of all. Those session IDs are going to be unique and random number again. So you cannot use the same session ID for other sessions. Or you cannot use this packet sequence number for the next packages. And they are selecting those numbers randomly. and they are incrementing by 1, okay, for the next packages that they are transmitting. Sometimes, hey, there could be some accident that you select the sound packet sequence number it's used before. Okay? If that is the case, destination is going to reject it. Okay? And destination will send to you an information saying that your packet is rejected because of packet sequence number. Please resend your packet. Okay? The idea is very simple. So we're going to always use this packet sequence numbers. By the way, what is the sequence number size that we are using in computer networks? 128 bits. Am I right? So anyway, check it, all right, and see what is the size of the sequence numbers that we are using in TCP/IP protocols. All right. So anyway, we're going to use those kinds of sequence numbers to make the packet unit. Right. We did that. So plain text will have the sequence number, okay, and by using the sequence number, we're going to construct the IV and counters that we're going to use in encryption. So that first of all, we're going to compute the MAC in CBC mode with AES algorithm. Okay? And for that one, I'm going to use this key. Okay, I'm doing this CBC mode. In other words, I'm encrypting the plain text with the sequence number, okay, encrypting it in CBC mode, and I'm taking the last block of the encryption as MAC. What is the size of MAC then? Last block of the encryption of AES is going to be 128 bits. Okay, 128 bits. So we have the MAC, and this key is used for the MAC. Okay, this key is used for the MAC. Clear so far? Okay. And then MAC is appended to the plain text. Counter values established, and then we're going to encrypt the MAC and the sequence number and the plain text, all of them, okay, in counter mode by using the same key that is used in MAC, okay, and the result is going to be your ciphertext. Yeah. No, you are encrypting the whole plain text. Only the last ciphertext block is your MAC. Okay, but you are generating the whole ciphertext blocks until to get last cipher, because last ciphertext block depends on all the previous ciphertext blocks. Why they are using it this mode, by the way? Why they are calculating MAC in CBC mode? Remember, when we discussed this MAC and hashes, we said that MAC and hash must be unique for a given plain text, right? How are you going to provide that kind of uniqueness? If you look at this calculation, you are encrypting your plain text, you are generating something totally random, because outputs of the encryption algorithms are quite random, all right? And then you are making your second plain text block by adding second plain text block to this random number. You are making your plain text block more random, okay? And encrypting that stuff, generating another random number. But the important thing is right now, this random number is a function of previous plain text and previous ciphertext blocks. And when we come to the last MAC, so the last MAC is a function of every bit. It's a function of every bit in the plain text. Every bit in the plain text. If you change one bit in the plain text, you're going to have totally different output over here. It's going to provide very good uniqueness. Okay? That's why this calculation is quite good and quite secure. And it is really, and the size is quite okay. It is 128 bit, because to the power 128 possible outputs, one of them is going to define your plain text, and to the power 128 is a huge number, by the way. And is there any chance that you may find a MAC, same MAC with a different plain text? Possibility must be very low to say that this is quite a secure MAC algorithm. Okay? For this kind of calculation in AES, okay, let me put it this way. There's very well known paradox. It's called birthday paradox. Okay, it's a birthday paradox. And the question in birthday paradox is this. How many students I should have in this classroom, number of students I should have in this classroom, so that I can find at least 2 students whose birthday is the same with the probability more than 50%. Okay. How many students should I have in this classroom so that I can hit or I can find 2 students whose birthdays, okay, are the same with the probability more than 50%. With the probability more than 50%. And I'm going to rephrase this question with MAC. What is the output of MAC? 128 bits. Okay, 128 bits. So how many different plain texts should I try? Okay, should I try? So that I can have same MAC with the probability more than 50%. How many different plain texts or the version of same plain text I should try to get the same MAC with the probability more than 50%? This is called birthday attack. I mean the birthday paradox. Yeah. To the power? Not really. And then this thing is not easy to calculate, by the way. It's not like this. It requires huge math, actually, probability and everything. Well, anyway, they calculated it, okay, and they found this result. Actually, you should try 2 to the power m divided by 2. M is the size or the length of the MAC, or the hash output. If it is 128, okay, 96 to the power 96 variations of the plain text that you can try, if you try, but this is a huge number, 2 to the power 96, okay? And then you may get 2 plain texts, different plain texts, produce the same MAC with the probability more than 50%. But still we are not saying that you're going to get it. We are saying that your chance to get is more than 50%. And how many variations of the same message you have to try? 2 to the power 96. It's huge. And today's standard for this kind of thing, we use HMAC, okay, and as I described earlier, SHA 512. 512 is the size of the hash or MAC, okay. So that how many you should try different plain texts? 2 to the power 512 divided by 2. Huge number. So you see, I'm not saying that it is impossible to find 2 different messages that is going to produce the same MAC, but what I'm saying that most probably it is infeasible. It is infeasible. First of all, how are you going to generate variations of the same plain text, 2 to the power 96 variations of the same plain text? Huge job. So that's why I can say that this is quite secure. And this is called birthday paradox, as I said. I mean, if you are interested, go and find some details for the birthday paradox for your e-portfolios, okay? So that you can measure the security of these guys. Okay? Right, anyway. So now we have the MAC and we're going to encrypt everything in counter mode, okay, in counter mode by using AES algorithm. Other important thing, key that is used for MAC calculation and key that is used for the encryption is the same key. We don't have any separate MAC key or any separate encryption key, basically. Okay? So this is the long-term solution. So as you see, they changed everything. Okay? Now your algorithm is AES for MAC calculation and AES for encryption. That requires hardware change. It is not just upgrading, uploading some software anymore. Now you have to go and buy a new modem, okay? New wireless modem, if you want to use CCRP. It changes totally everything. because those guys got fed up most probably with this WEP. Okay, play with this one, or make this key a little bit random, make this, but you are not actually solving the actual drawbacks of WEP. You are just making WEP a little bit stronger. So that's why they say that, hey, okay, we got enough, so let's move and let's change everything. And as far as performance is concerned, implementation of AES algorithm is very, very fast algorithm, by the way. Okay, hardware, software implementations. You're gonna have only 4 tables, 4K size, 4K tables. That's it. It's nothing. So that compared to RC4, it is as fast as RC4. That is the other reason that they decided to use AES. And also RC4 was not a standard. AES is a standard, industry standard for encryption. And it is pretty secure algorithm. So far, nobody managed to break that algorithm. And it comes with the option to 156-bit key size. Okay, so if the 128-bit is no longer secure enough, you can move to 256-bit key sizes. Okay, so in other words, it accommodates the future as well. So that's the idea. Okay, then you got your ciphertext, and then when we got the ciphertext, the destination side is going to recompute the MAC from the plaintext. First of all, it's gonna decipher the message, and it's going to get the MAC and encode it. It's going to get the MAC and packet and the packet sequence number. It's going to check packet sequence number whether this is a reply message or a new message. If it's a new message, it's going to recalculate the MAC with the same key that is used for the source size, from the source size. Okay? And then if the MACs are the same, recalculated and received MACs, then this integrity is okay, message is accepted, and then whatever you're going to read in the plain text, whatever the plain text says, you're going to do that one. So that is the whole working order in the destination side. So you may ask this, how the destination knows this integrity key and this confidentiality key. We are using what? IEEE 802.1x. Again, same protocol. Okay, same protocol that we use in CCRP. Okay? TKIP, I'm sorry. So CCRP employs a 48-bit IV. So IV size is 48 bits. Okay? And this as sequence number. Okay? And provide replay detection. Okay? Ensures the lifetime of AES key is longer than any possible association, basically. And the key management confined to beginning of association and ignores this lifetime. Okay? They are using AES. Okay? And we don't need per packet key. Right now, we are just generating the key. We are using the AES key for packet key anyway. Okay? Use the same AES key to provide confidentiality and integrity, as I said. And uses an 8-octet MIC. We said that output of this one is 128-bit, right? 8-octet is equal to what? 64. So they are not using total 128-bit because if you increase the size of the message that you are transmitting in wireless environments, most of the energy that you are spending is going to go to the transmission. If you are transmitting long messages, that means you need more transmission power. That means your battery life is going to get shorter. So that's why you have to find an optimum stuff. So for example, you cannot go and say that, hey, if the birthday paradox tells me that the size of the MAC, if it is bigger, more security, hey, I'm going to use 1024-bit for the MAC size. You cannot do that because that means that you are increasing your packet size 1K. Okay? 1K increase in your packet size that you're going to transmit. Now your battery or your transmission, the system is going to require more power to transmit that message. And your battery life is going to get a little bit shorter. We don't want to have those kind of problems in wireless environment. Don't forget, wireless environments are always power limited, right? Computation limited, and memory limited. All right, so that's why They are just using 64-bit oversharing. 64-bit is more than enough anyway. Again, if you look at the birthday paradox, this time you have to find 2 to the power 32 different variations of the same message. Again, check that number. You will see that it is a huge, 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 huge number. 2 to the power 32. All right. And it is stronger than Michael. Yes? Yeah. It uses the same key with the integrity and confidentiality. Yes, true.
Let's say somehow the key is compromised.
Then you are going to be in trouble. If key is compromised, algorithms are known, okay, and then they are going to, first of all, they are going to see the content of your message, plain text.
And they can calculate MAC also.
Well, MAC calculation is not going to harm you. If they know your MAC, you are not revealing any security-related information about your plain text if your plain text is confidential, right?
Yeah, but if they can see the MAC, it means they know the key, and then they can change the message and they can recalculate the MAC.
That's the thing, definitely. They can change the message and they can calculate a new MAC. And then this way they can actually implant a foster message to the system. Yes, that is a drawback, definitely. But hey, if you are losing your key, if there is a key compromise, you don't have any security system anyway.
Yeah, but in that case, here someone might know the key and he might not know that there's somewhere.
I understand. You are saying that if you are using 2 different keys, if there's one compromise, the other one may provide some level of security. Yeah, exactly. But for this kind of applications, this is more than enough. Because, okay, again, you have to look the advantages and disadvantages. As you say, if there's any compromise, you are losing your integrity and confidentiality services together. If you are using 2 different keys, whatever the key is compromised, you are losing only one service. You are absolutely right with that one. But this time you have to generate 2 keys. You have to manage those 2 keys. You have to distribute those 2 keys instead of 1 key. Right? Again, this time management is going to be a little bit problematic. But for this kind of environment, this is more than enough. Okay? More than enough. And key size is quite enough. But in security, if you are not protecting your keys, you are not going to get any security services at all. And by the way, based on your question, if they know my MAC, okay, and as you said, they can recalculate it. But imagine that MAC is known, but key is not known. Key is not known. This MAC information is not going to reveal any information about your plain text. These functions are called one-way trapdoor functions. So you can go into this classroom, okay, but you cannot get out of this classroom kind of stuff. Okay, if the door is one-way door. Okay? So these are like that. But if you guys develop something new, saying that, okay, I can actually get original message just by using last block of the encryption, that is the MAC, you're going to be the richest guy in the world, because imagine that every packet that you are transmitting, no matter what size your plain text is, with 64 bits. Fixed packet size in computer networks. Everything is 64 bits. Either your message is 1 gigabyte message or 1 terabyte message. Can you imagine the implications? Yep. Well, so those things are one-way. Hash functions and MAC functions are always one-way. It does not reveal anything about your plain text. Okay? Right. What else? Let's compare these guys. So what we saw so far is this. WEP. They are using RC4, right? RC4 algorithm. 40 or 104-bit encryption keys. TKIP, again RC4, 128-bit encryption, but with the key mixing, actual stuff is same. And 64-bit authentication. For the CCRP, AES, 128-bit key size. Key lifetime, in other words, per packet key, 24-bit wrapping IV, concatenated IV to base key, to make the key a little bit longer. In TKIP, 48-bit IV, sequence number, in the mixing function. Okay. And over here, 48-bit IV, but no mixing function. We don't need mixing function at all. Integrity in WEP, packet header, no, we don't have any packet header, but they are using CRC as a trailer. Okay? Source and destination address protected by Michael over here. Okay? And in CCMP, we are using counter mode MAC. Okay, counter mode MAC, that is AES. Okay, that is AES. Packet data replay detection, CRC32 and none. They are not checking any replay over here. And Michael and enforced IV sequencing. So 48-bit IV is used over here for packet sequencing. Again, CCMP MAC IV sequencing. Again, we are using 48-bit IV to make each packet unique. All right, key management in WEP. Do we have any key management in WEP? No. And TKIP came up with IEEE 802.1x, and CCMP is using, again, IEEE 802.1x. So this is the whole summary that we covered so far. This part, TKIP, CCMP part, is called IEEE 802.11i protocol. Okay, IEEE 802.11i protocol. With I, they came up with TKIP and CCMP solution. Are we clear? Okay, so we said that at the beginning, in this chapter, we ask some questions, right? And let's have a look at those questions. Can VLANs become completely secure? Okay, based on this knowledge right now, TKIP, CCMP, and WEP, what do you think? Do you think that VLANs become completely secure? No, it cannot be completely secure, but through a collection of countermeasures, like these MAC calculations, IVs, packet sequences, adequate security can be achieved anyway. And I believe that with TKIP, CCMP, we have the adequate security right now. Okay. It's not perfect. Nobody is saying perfect, but it is adequate. So in other words, it's okay for us. Okay, it's okay for us. Can organizations that handle private customer information, such as banks, hospitals, government, integrate VLANs within their organization with the wired networks without compromising private and sensitive information? Answer? Well, this is my answers. You may not agree with that one. Okay? I'm not saying that this is correct. I'm saying that based on my experience, based on the information that I just learned, hey, yes, it can be. Okay? But not as extension of the wired network for now. Okay? And and should be deployed outside of the wired networks, blah, blah. What does the future hold for VLANs? No future. Right? Right. That's my opinion. But hey, that's not correct. The future of LANs looks bright. Well, anyway, you guys are experiencing this stuff right now, right? Everything becomes wireless, okay? And it's already deployed in coffee shops, and even Walmart is having this kind of technology right now, okay? So will VLANs make wired networks obsolete? What do you think? Do you think that it's going to be obsolete, wired networks? Well, you never know, right? Maybe not in the very near future, but in the long term, they may replace these wired networks. But for the near future, I should say, no, they are going to work together. They are going to work together. Because still wired networks are much more faster than wireless networks. And we don't have proper broadband solutions for the wireless networks as well. So in other words, wireless networks are still in developing stage. Okay? So if we have proper broadband wireless network, and if we have proper security solutions to the wireless environments, if we can solve these power problems, limited memory problems, and if we can solve the problems comes from mobility, we will see in the next chapter anyway. Okay? Then these things are going to replace wired environments. Okay? Can VLANs become commercially successful? Hey, it's already a success story anyway.